Before X-rays can be produced, the imaging system must take incoming electrical energy and convert it into the specific electrical conditions required by the X-ray tube. That is the primary role of the X-ray generator. In this lesson, we'll look at the operating console, the major electrical circuits, transformers, and rectification. Then we'll connect these concepts to the actual production X-rays. The operating console is where the radiologic technologist controls the exposure. From the console, we select exposure factors such as KVP, MA, and exposure time. KVP primarily controls the energy and penetrating ability of the X-ray beam. Milliampere, or MA, controls the number of electrons flowing from the cathode to the anode, while exposure time determines how long that electron flow occurs. When automatic exposure control, or AEC, is used, the system automatically terminates the exposure once sufficient radiation reaches the image receptor. The X-ray generator contains three major electrical circuits: the primary circuit, the secondary circuit, and the filament circuit. The primary circuit receives incoming electrical power and includes components that help control the voltage supplied to the system. The secondary circuit provides the high voltage necessary to accelerate electrons across the X-ray tube. The filament circuit provides the current needed to heat the cathode filament, allowing electrons to be released through thermionic emission. An easy way to organize these concepts is: primary controls the incoming power, secondary provides high voltage, and filament provides heat for electron production. Transformers regulate electrical energy by changing voltage and current. Two important transformers in the X-ray circuit are the step-down transformer and the step-up transformer. The step-down transformer decreases voltage while increasing current. This is important in the filament circuit because the tungsten filament requires relatively low voltage but high current to generate enough heat for thermionic emission. The step-up transformer does the opposite. It dramatically increases voltage while decreasing current. This produces the KVP needed to accelerate electrons from the cathode toward the anode. Another essential function of the generator is rectification. Electrical power enters the system as alternating current, or AC. With alternating current, the direction of electron flow periodically reverses. But inside the X-ray tube, we need electrons to travel in only one direction, from the cathode toward the anode. Rectifiers accomplish this by converting alternating current into direct current, or DC. This prevents electrons from traveling backward through the X-ray tube and ensures that electron flow occurs in the direction necessary for X-ray production. Not all rectification systems produce the same voltage waveform. As we move from half-wave to full-wave, three-phase, and high-frequency generators, the electrical output becomes progressively more efficient and consistent. The key concept here is voltage ripple. Voltage ripple describes how much the voltage fluctuates during an exposure. A high voltage ripple means greater variation in the voltage applied across the X-ray tube. A lower ripple means the voltage remains closer to the selected KVP throughout the exposure. Modern high-frequency generators produce very low voltage ripple, resulting in a more consistent and efficient X-ray beam. Keep this relationship in mind. Lower voltage ripple means a more consistent tube potential and more efficient X-ray production. Let's begin with half-wave rectification. Half-wave rectification uses only one half of each alternating current cycle. The opposite half of the cycle is blocked. With a 60 Hz electrical supply, this produces approximately 60 useful pulses per second. Because half of the electrical cycle is not being used, half-wave rectification is inefficient and has a 100% voltage ripple. The voltage repeatedly rises to its peak and then falls back toward zero. Because of this high ripple and low efficiency, half-wave rectification is rarely used in modern diagnostic imaging systems. Full-wave rectification improves efficiency by using both halves of the AC cycle. Instead of blocking the negative portion, the rectifier flips it so that electron flow remains in the required direction. This gives us 2 useful pulses per cycle. With a 60 Hz electrical supply, full-wave rectification therefore produces 120 pulses per second. Although the voltage ripple is still high, full-wave rectification uses the incoming electrical supply more efficiently than half-wave rectification. This type of system is associated primarily with older X-ray equipment. Three-phase systems improve generator efficiency even further. Instead of using a single AC waveform, three-phase power uses three alternating waveforms that are 120 degrees apart. Because these waveforms overlap, the tube voltage does not fall all the way back to zero between pulses. In a three-phase, six-pulse system, there are six pulses per cycle. At 60 hertz, that produces approximately 360 pulses per second. The result is a much lower voltage ripple, approximately 13 to 14% in a six-pulse system. Compared with single-phase equipment, the voltage remains much closer to the selected kVp, creating a more consistent and efficient X-ray beam. The process begins with heating the tungsten filament to approximately 2,200 degrees Celsius. This leads to thermionic emission, releasing electrons. High voltage then accelerates these electrons towards the rotating anode. Upon collision, X-ray photons and heat are produced, completing the process. Once the accelerated electrons strike the tungsten target, X-rays are primarily produced through two interactions, Bremsstrahlung radiation and characteristic radiation. Both interactions contribute to the diagnostic X-ray beam. The important connection is that the generator creates the electrical conditions necessary for these interactions to occur inside the X-ray tube. From the operating console to the final production of X-ray photons, the generator controls and modifies the electrical energy needed to produce a useful X-ray beam. Remember the major concepts. The filament circuit provides the heat, the step-up transformer provides the high voltage, kVp, rectification, keeps electrons moving from cathode to anode, and the generator waveform determines how consistently the voltage is delivered. Understanding this sequence gives you a strong foundation for understanding X-ray production and many of the generator concepts you'll encounter in radiographic physics.